This is a discussion on acid-base disorders. So first of all, you need to know what's normal. These are the normal values. I would commit them to memory. One thing that's nice about it, if you put it in this order, it kind of decreases by size. So for example, the first number there is 140. You see 140 is the biggest. Okay, chlorine, so sodium 140, chlorine, basically just swap the 0 and the 4. That's kind of nice. So 140 for sodium, 104 for chlorine. Just swap the 4. Next one, we keep that 4, and I don't know. Basically, just know that CO2 is 40. Okay, so sodium was 104. This one's 40. So lots of zeros and 4s, just going down in size. This was the biggest number. Next one, biggest. Next biggest. This one's just 40. And this next one, 24. Okay, so it's almost like about half of normal for CO2. If you notice, the normal for CO2 was 35 to 45. This one's like almost half of the big end of it. So 24, but again, lots of 4s in here. Next one, pH, normal 7.4. But you need to know the range. So basically add 5, take away 5. Or I guess 0.05. So 7.4 is normal. Add or take away 5. And you don't really need to know these other ones, but just know it's 4. So more 4s, lots of 4s in here. Okay, now here are the steps, and you will need to memorize these steps. These steps are important, and I'll talk through them real quick. First thing you do is check the pH. So the pH is less than 7.4. I think it's really less than 7.35. You're dealing with some sort of acid disorder. So it has to have the word acid in it if it's less than 7.35. Acidosis. Next, you check the CO2. CO2 is going to tell you whether or not you are respiratory or metabolic in a lot of this kind of stuff. So we'll go through that in a second. Then you're going to check the appropriate compensation formula. I'll show those in a little bit, how that works. After you check the appropriate compensation formula, then you're going to determine if the compensation is appropriate. Once you determine if the compensation is appropriate, then you're going to check the anion gap. And I'll show you how to do that as well. If the anion gap is elevated, check the delta-delta. If a metabolic acidosis is present, check the urine pH. And I'll tell you if you have renal tubular acidosis. If the urine pH is greater than 6 and the blood pH is less than 7.34, then you're dealing with a renal tubular acidosis. Or alkalosis, I can't remember. RTA. That's from memory. Hopefully I didn't make a mistake there. Generate a differential diagnosis at this point. And I'll talk about how to do that as well. Okay, so first of all here, this is kind of walking through it. Alright, so first of all, the person has a pH of 7.35 and their PCO2 is less than 40, which means, in other words, they're not holding their breath and keeping all their CO2 in. Because if they're holding their breath and keeping all their CO2 in, then we'd be dealing with a respiratory issue, because it means it has something to do with the fact that they're not breathing. So they have their low pH, and it's not caused from holding their breath. So that means it's not respiratory, it must be metabolic. And you know it's acidic because this is less than 7.35. So what do they have? Well, you need to do. They have metabolic acidosis, but now you need to determine, is their respiratory compensation adequate? So what you do is you take the PCO2, and if it is equal to 1.5 times HCO3, an easy way I think to do that is basically take HCO3 and then add it to half the HCO3, and then you add 8 to that. And if that is equal to the PCO2, then you would say, it's adequate. They have adequate respiratory compensation. But if it's not about equal to that, you'd say, not adequate respiratory compensation. Next step. And I'll work through these in problems, so you'll see how this works. Next step. Or not next step. Different situation. Let's say in this one, the pH is greater than 7.45. Well, now we're dealing with an alkalosis. We know that right off the bat. We can put alkalosis in our answer. Easy. Now you look at the PCO2. The PCO2 is greater than 40. So if they've got high PCO2, you'd think they'd be acidic, right? Because PCO2 makes people acidic. But wait, they're not acidic, they're alkalinic. So if a person's alkalinic, but they have a CO2 that should be acidic, because normally you'd think that a person has a high CO2, greater than 40, maybe they're holding their breath, but they're not. We already determined, well, they're not acidic, so this must have something to do with something else in the body. Well, what's another process that happens in the body that determines your alkalinity or acidity besides breathing? That would be your bicarb levels. HCO3 is your bicarb, it was discussed up here too. And what is happening here is the person has excess bicarb in their blood. And the PCO2 must just try to be compensated for that or something. I don't know. So excess bicarb must be accounting for this pH being greater than 7.45. Because it's all about your bicarb and your CO2 basically determining what your acidity or alkalinity is. So if it's bicarb, then we're saying, all right, this person has a metabolic issue. So they have metabolic alkalosis because this is not determining their pH. Something else is determining their pH. So they have metabolic alkalosis because they have alkalinic blood and it's not being altered by this CO2, altered by something else. I guess determined. I'm sure it's being altered by that, but not determined. So they have metabolic alkalosis. So now what are you going to do? You're going to find out if that is compensating at all. So you take your PCO2 and, you take your HCO3 and you add it to 15. And if these two numbers together are about equal to this, then you'd say, they have adequate respiratory compensation. But if it doesn't about equal that, then you'd say, not adequate respiratory compensation. Okay, hopefully you're following this. We'll go through problems, it'll make more sense in a little bit. So next, pH, less than 7.35, and PCO2 greater than 40. So acidic, and oh look, this is more than normal, and that means that if these two, this is acidic and this is greater than 40, you say, well, this stuff, CO2, is acidic, so what must be going on here is their acidity is determined by their fact they're holding their breath or something. So this is respiratory acidosis, and the PCO2 change. So now you know it's respiratory acidosis. Now what you want to do is you find out, is it chronic or is it acute? So what you do is you look at the PCO change. Is the change in PCO2 greater than normal? Okay, so you take normal PCO2, and is it for every 10 above normal that it is? Because it says it's above normal here. So if let's say it was 50, then the HCO3 must have changed at least 1. Okay, so let's say you look at your CO2 and it's 40, and your HCO3 normally should be 24, if you remember. So let's say that should be about 25. So if your PCO2 was 50 and your HCO3 was 45 about, then you'd say, this is an acute respiratory acidosis. Okay? Look at different circumstance. What do you look at this? Okay, same thing. Yeah, this is acidic. This is causing the acidity. We got respiratory acidosis. Now look at our PCO2 change, and we see, okay, so for every 10 that my PCO2 changes, so let's say it's 50 here, and my HCO3 is going to change by 4 in this instance. So let's say this was 50, and my HCO2 is going to be 24 plus 4, so it'd be about 28. So if I had an HCO3 of 28 and a CO2 of 50, then I would say this is chronic. What do I mean by chronic? It means that the person has had a respiratory acidosis for so long that their kidneys have finally kicked in, and you have some metabolic compensation. Their kidneys have kicked in, and they're altering the amount of HCO3 in the body because this is elevated more than one ratio. Now this doesn't have to be just one level. I mean, this could be the change could be 2 changes of 10 or whatever. So it could be something like 60. Okay, so let's say this was 60. It means that the HCO3 would need to be 24 plus 4 plus 4. So that'd be, what is that, 32. So if it's 60 and 32, same thing. We'd say it's chronic. Or it could be something in between there, or something more, something less. Could be 73 and whatever. But anyway, you need to figure out the ratio, whatever it is, break it down, see if it's a 10 to 4 ratio chronic, 10 to 1 ratio acute. Okay, now we can do the same thing with alkalosis, basically exactly the same process. Hopefully you're getting the hang of this now. Look, this is above 7.45 alkalosis. This PCO2 is less than 40. So you'd say, okay, the person must be, this is below normal, so the person must be breathing really fast, like they just kicked out a whole bunch of CO2 when they did that. So now they have really low CO2, and their pH is really high, which means it's really alkalinic. So they have a respiratory, the respirations are determining the alkalinity of their serum, their blood, and so they have respiratory alkalosis. It's the same in both these instances, but here's the difference here, same as the other one. PCO2 change of 10, so look at their PCO2. Their PCO2, let's say it's 30, then there should be a change of HCO3 by 1, okay? So the same instances before, and that you think of it could be, this one I think is 1 or 2 to be acute, and about 4 to be chronic. So same situation as before. You just calculate it out. Okay, so now you know whether or not they have metabolic acidosis, whether or not the compensation, respiratory compensation was adequate, or whether it was inadequate. And now you know, or I guess, sorry, not adequate or inadequate, whether it matches up to this. You know whether they have metabolic alkalosis, whether or not the respiratory compensation was adequate or inadequate. You got to remember this little equation here, 1.5. If they have metabolic acidosis, then you remember 1.5 HCO3 times HCO3 plus 8, and that'll give you a number. If that number equals the PCO2, then it's adequate. If it doesn't, then it's not adequate. Same thing over here. Remember that metabolic alkalosis. We got all these equations. We know whether they have metabolic acidosis, metabolic alkalosis, acute respiratory acidosis, or or chronic respiratory acidosis, acute respiratory alkalosis, or chronic respiratory alkalosis. We have that answer. Now what you do is you take the anion gaps. You take their sodium minus the combination of their bicarb and chlorine. You could just go sodium minus bicarb minus chlorine, or you can add them together in parentheses if you like to do algebra. And anyway, that's going to give your anion gap. If you look at your anion gap, and if the anion gap is elevated, which means if it's like bigger than 12, okay, 12 is normal, as long as that person has an albumin of 4. If the person has an albumin of 4, you can calculate the albumin. You take albumin times 3, and that should be a normal anion gap. That kind of determines the anion gap. But anyway, won't worry about that for now. But anyway, if the anion gap is greater than 12, then it's elevated. And then you can just say, that the person must have an anion gap metabolic acidosis. I guess you just know that somehow. Well, I guess they have an anion gap if you do that. Okay, so then you want to figure out the delta-delta ratio, or sometimes they call it the delta gap, whatever. What you do for that is you take the measured anion gap, what you just got, and you put that on top. And on bottom, you put the normal HCO3. So normal HCO3 should be like 24. You take the measured anion gap, and you subtract the normal anion gap from that. And then from the bottom one, you subtract the measured HCO3, so whatever they had, big or small, and then you're going to get your delta-delta. Okay? So now let's do a problem. Yay, we finally got the problems. So for this, bust out my pen. Let's solve this thing. So first of all, we'll look at this. pH. pH is low. So I know that whatever our answer is, it's going to have the word acid in it. So, well, now we got to figure out if this is respiratory or if this is metabolic. So we look at the PCO2. PCO2 is high. So that means that this person's acidity must be determined by this CO2 here. So what I would say is they have respiratory acidosis. Wow, that was extremely easy. So this was less than 7.3. This was greater than 40. It's going back to a really basic equation there. We understand that that equals respiratory acidosis. So now we got to find out if this is acute or chronic. Remember that 1:4 ratio? So now what we're going to do is we're going to look at our HCO3 and our CO2. So for every 10 that our CO2 is above 40, if it is acute, this will be 1, and if it's chronic, it'll be 4. So let's take a look at it. So this is 2 10s above 40, and that means that this number here should be about 2 above 24 if it's acute, and it should be about 2 4s, which would be 8 above if it was chronic. And you can already see here, this is clearly acute, but let's just say, what would it look like if it was chronic? If it was chronic, that would be 24 plus 2 4s, so it would be plus 8, so it would look like something like 32. Well, it's not about 32, it's 26, and so now we know this must be acute. So I've already determined from this is acute respiratory acidosis, as long as I'm not screwing anything up. I don't remember what the answers to these are. Okay, so now what are we supposed to do? It is, maybe you can stop there. I don't really know. I guess you could check the urine pH, whatever, but I think at this point, I think you've pretty much figured out it's acute respiratory acidosis. I guess you could, yeah. Let's see what the answers are for this thing. I mean, I guess if in the other instances, then next you check the anion gap. Well, let's go check the anion gap. So the anion gap, you take sodium. So I'll write up what we're going to do first. Take sodium minus chlorine plus HCO3 or bicarb. And that's going to equal your anion gap. Okay, so let's go ahead and do that. Let's take our I'll do it down here, I guess. 137. I should choose another color so you can actually see what I'm doing, huh? Let's try blue. Maybe that'll see a little better. 137 minus 100 plus 26. So basically 137 minus 126. And I'm not very good at doing math in my head, but I think that's like 11. What's a normal anion gap? Normal anion gap should be 12. Well, so that looks awfully close to 11 to me, close enough that I would say there is no real anion gaps. This would say non-anion gap. But we don't even know if there's I don't think there's even a metabolic compensation here, but I guess I could look here to see if there's any other metabolic stuff going on. So then what I would do, my next little equation, so let's see, I had to see if it was if the compensation, no, that's with another one. Okay, so sorry. Now what we need to do is, I guess the other step for this would be doing the delta-delta ratio. If you remember, that was the measured anion gap minus the normal anion gap. Put that over the normal HCO3 minus the measured HCO3, and that'll give us our delta-delta. So measured anion gap, I'll do this over here. Measured anion gap was 11 minus normal is 12 over normal HCO3. Normal HCO3 is normally 24 minus the measured. The measured is 26. So we get like what, negative 1 over 2. I guess that's our delta. Maybe I should, I'm not very good at fractions. I don't really hate math. But anyway, whatever. Not really helpful to us. So what is the prominent acid-base disorder? It was acute respiratory acidosis. Is the degree of compensation appropriate? We determined, we never even calculated that. Probably because it was metabolic or whatever, but I don't know. No? Yes. I guess there was no real anion gap, so yes. I don't really know. Is there another disorder present? Not that I could see. What is the differential diagnosis? Well, if a person, that's really the case here, 26-year-old man, known past medical history, ambulance after friends, unresponsive apartment. He had last been seen at a party 4 hours prior. So if he's at a party, we're probably thinking drugs and alcohol, I'm guessing. Especially since he has respiratory acidosis. Usually you get respiratory acidosis when you stop breathing, and narcotics. Narcotics tend to slow your breathing down, which will make you respiratory acidotic. So let's see if I'm right. I could be totally off, but we'll learn from it either way. So respiratory acidosis, acute, we got that. Degree of compensation appropriate, we said yes. Is there another disorder present? We said no. The combination of acute respiratory acidosis and non-responsive conduction is highly suggestive of drug intoxication. So yeah, so we got the right idea. This guy was doing drugs. Okay, next case here. 67-year-old man with type 2 diabetes, diabetic nephropathy, and chronic kidney disease, stage 3, presents for routine clinical visit. He is currently asymptomatic because of some abnormalities on his routine blood chemistries. You elect to send him for an arterial blood gas. So let's see what he's got here. First of all, that's the lower limit of acidic, so he's probably acidic. And his PCO2 is also low. Interesting. So if that's that would be like the easy way to kind of tell what's going on here. So if his if this is low, his pH is low, and his PCO2 is low, then that means his pH must not be determined by his PCO2, which means it must be determined by bicarb. So in this instance, I would say this is metabolic, because those aren't really matching up very well together. So it's metabolic acidosis. So metabolic acidosis. Okay, next step. Well, now that I think it's metabolic acidosis, now I'm going to use that little equation thing that I talked about earlier, which was the 1.5 times bicarb plus 8. Okay, so this, it would tell me whether or not he had, I don't know, his body was compensating or whatever. So that's what I do for metabolic acidosis. What if it was metabolic alkalosis? What if this was really high, like 7.45 or 7.5 or something like that? Well, then I would have used a different equation. I would have used the one that was the HCO3 plus 15, and then I could have seen if his thing was adequate. Anyways, but we're not. We're doing this one here. So 1.5 times HCO3. So where's his HCO3? We're looking at 18. So we got 18. So we multiply that times 1.5. So the easy way that I like to do that is basically just 18 and then half of 18. So 18 plus 9, what is that, 27. So we got 27, and then we're going to add 8 to 27. So 8 plus 8 would be 16, so 8 plus 7 must be 15, so 15 plus 20 is 35. So 35 is the number that we're getting here. And then we're going to compare that to his PCO2, which is 34. I think 35 is awfully close to 34. So I would say that it is adequate compensation. So it's compensate, yes. Comp, yes. Now what we're going to do is we're going to check his anion gap, see what's going on there. So remember, the anion gap is going to be sodium minus chlorine plus HCO3. Oops, chlorine. So now we throw the numbers in there. 135 minus 110 plus 16. What do we get? 135 minus 126. So if this was 125, that'd be easy. The answer would be 10, but it's not quite that. It's one more than that, so the answer is 9. So the answer is 9 here for his anion gap. Anion gap equals 9. And so he does not have, if it was greater than 12, then I would have said that he had, anion gap metabolic acidosis, but I'm not seeing that. So this is a non-anion gap. Now what I'm going to do is I'm going to figure out his delta-delta. So I'm going to take his measured anion gap, which is 9, and I'm going to put it over his, actually I'll probably write what I'm going to do first so that you can see. So I take measured anion gap over his normal HCO3, and I subtract his normal, what would be a normal anion gap, and I do it so it's normal HCO3 minus measured HCO3, and find out what that is. So let's throw in some numbers. Measured anion gap is 9 minus his normal anion gap, which is 12, and then normal HCO3 over his measured HCO3. So his HCO3 is 16 minus the measured, normal HCO3 is 24 over his measured, which is 16. Let's find out what that ratio is. 9 minus 12, -3, 24 minus 16. If this was 26 minus 16, it would be 10, but it's going to be 2 less than that, so it's going to be 8. So it's 3 over 8. I guess that's my delta-delta. I don't even really know what that means at this point. Whatever. So now what I'm going to do is I'm going to see if I got the right answers for this thing. So is the predominant, what is it? Predominant acid-base disorder? I would say non-anion gap metabolic acidosis. Is the degree of compensation appropriate? Did we calculate that? Yeah, we did. What was it again? I think it was yes. Yeah. Yes. Is there another disorder present? Not that I could find. What is the differential diagnosis? So what do we got here? Metabolic, non-anion gap metabolic acidosis. So let me share with you real quickly my little mnemonic. Hopefully it'll be helpful for you. So if you want to aggravate, if you want to nag, if you want to nag your ma, how are you going to nag your ma? You're going to say, I want your card. I want your card, Mom. I want your card. Like your debit card or whatever. Nag your ma by saying, I want your card, Mom. So what does this I card stand for? First of all, NAG, Ma, stands for non-anion gap metabolic acidosis. So then I card stands for isopropyl alcohol, I can't remember all these off the top of my head. Oh, this is bad. I may have to look it up. I think this was diarrhea. Yeah, I'm probably going to have to look this up. I think this is Addison's. That could have been diabetes. Hold on, let me look this up. Go in here, pull up my key. I don't want to steer you guys wrong. Oh, wrong one. It's for my CIL. Okay, so going down here. There we go. Metabolic acidosis. Okay, so here's the card one. So it's isopropyl alcohol, carbonic anhydrase inhibitors, like acetazolamide, Addison's disease, renal tubular disease, acidosis, excuse me, and diarrhea, especially type 4 apparently. Okay, so let's go back to where we were. So this was renal tubular disease. This was Addison's. And this was carbonic anhydrase inhibitors. And the last one was diarrhea. Good. Okay. Carbonic anhydrase. Yeah. So like acetazolamide. So that's what you do. So our differential for this guy, since he was, he had diabetes, type 2, diabetic nephropathy, okay, CKD, stage 3. Okay, so this guy's got problems with his, he's probably got diabetes-induced chronic kidney disease. So I'm going to say he's probably got this renal tubular acidosis. So differential diagnosis is, renal tubular acidosis, probably type 4. And why is the patient hyperkalemic? Probably has something to do with his tubes in his kidney dumping out too much potassium, but I don't know, or I'm holding on to potassium, but I'm not really sure. Let's see what they say. Okay, so prominent acid-base disorder. I was correct. Non-GAP metabolic acidosis. Is the degree of appropriate? Yes. Is there another disorder? No. So I got all that right. Okay, what's the differential diagnosis? It says the low urine pH. Did they give us urine pH on there? Yeah. Okay, whatever. Oh, yeah, urine pH. Look at that. Lower, less than 6. The urine pH is less than 6. Then you're thinking if he has a pH that's also about less than 7.35 or close to there, you're thinking the renal tubular acidosis. So that was the case. So this particular fellow, you would have thought that based on his low pH and whatnot. Okay, so yeah, so low urine, renal tubular acidosis. This guy, type 4. So what do we think he has? So it says there's nothing in history suggesting etiology type 1. So you don't think he has type 1 or type 2. However, patients with diabetes develop type 4. So type 4 is the one that causes diabetes. Type 4 renal tubular acidosis due to hypoaldosteronism, which leads to impaired secretion in the distal tubule. So it looks like this guy actually had aldosterone issues, which I think was the A in card has Addison's. So that was probably related to that. So there we go. So why is he hyperkalemic? Probably has to do with his Addison's type issue. I believe that aldosterone, I know that aldosterone antagonists are also called aldosterone. Antagonists are also called potassium sparing, which means that they hold on to potassium, which means your potassium spikes. So aldosterone itself actually decreases the amount of potassium. So if this guy is aldosterone deficient, which is kind of what happens, I think, in Addison's, something like that, that means that he would be having almost the equivalent as if he was taking aldosterone antagonist, which means he's going to have high potassium. So let's see if that's what this says. Hyperkalemia is due to impaired secretion of potassium in the distal tubule as a consequence of low aldosterone. So yep, there it is. All right, next case. Hopefully these are starting to come together. Can you think of what to do in this case? What's the first thing that you would do? What are you going to check first? That's right, you check the pH. The pH, is that high or low? Correct, it is high. So whatever our answer is going to have, it's going to have alkalosis in it. At least for the primary one. Alkalosis. I hopefully you can read what I said there. Okay, now what are you going to look at? That's right, you're going to look at the PCO2. Is the PCO2 above or below what number? That number is 24. And is it above a 24? Yes, it is. So greater than 24. Now, there's this little acronym I'm going to teach you right now that's kind of nice. It goes respiratory opposite, metabolic same. Respiratory opposite, metabolic same. ROAM. Okay? So, in respiratory conditions, the pH and the PCO2 are going to be going in opposite directions. Opposite directions. These arrows are not going in opposite directions. They're going in equal directions or the same directions. Sorry, I said same earlier and I put an E up there. Equal directions, okay? So now we're going to look here and we're going to see metabolic equal or same direction. Equal. So these two arrows are going in equal directions, the same direction. So we're going to say this is metabolic, okay? So what do you know? We know already this is metabolic alkalosis. And now that you've been working the past few questions, logically thinking through why this is, now you have an acronym to help you in case you forget the logic behind it or get too stressed out to remember the logic behind it. Basically, you look at the CO2. This guy's CO2 is high, which normally would cause acidosis. But since this guy's is not acidotic, you must be saying that his pH is determined by something other than his CO2. They don't match up, in other words. So what you'd say then is this must not be determined by CO2. If it's not determined by CO2, then it's not a respiratory issue. It must be a metabolic issue. It must be determined by his bicarb. So, oh, you know what? I realized I just totally made a mistake. Well, now you learn a handy acronym. Now forget it, because PCO2, this is one of the reasons why it's really important to memorize those first numbers I gave you. PCO2 is supposed to be 40. Oh man, it's HCO3 that's supposed to be 24. Woo, big mistake. So let's erase whatever the heck we were just talking about and go back to square one on this one. And sometimes you make mistakes like this and it really costs you big. So at least I do. So is his PCO2 less than or greater than 40? Well, clearly it's way less than 40, so which means it's decreased. Whoa, that means we've got respiratory because these are going in opposite directions. So we have respiratory alkalosis. Respiratory alkalosis. Okay, whew, big mistake there. Okay, now what's the next thing we're going to do? We looked at his pH. We looked at his CO2, and now we need to check our what? We need to see if this is acute or if it's chronic. Okay, is this acute respiratory alkalosis or is it chronic respiratory alkalosis? Remember how to do that. You compare his bicarb to his HCO3. Okay, so what is his CO2? What is his bicarb and what's normal? So his CO2 is 28 and his goodness gracious. Whew. I'm making all kinds of wonderful mistakes today, huh? Her HCO3 is 21. Wow, that's like a 1-to-1 ratio. Well, if it's a 1-to-1 ratio, it's definitely not a 10-to-1. I guess. Sorry, I screwed up. You're not supposed to do the 1-to-1 ratio thing. Man, I'm really goofing up today. You're supposed to say that for every 10 changes, for every 10, So this is approximately close to 30, which is, so 110 below. So for every 10, this should have changed. This should have changed by 1 if it is acute, and it should have changed by 4 if it's chronic. So let's see here. So this did change about 10, and this then from 24, if it had changed 1, then we would say, okay, it would be at like 23. If it had changed 2 or 2 of these things down, or I guess 2 20s, we'd say it'd be at 22. And if it had changed, like 30, then we'd say that it should be at 21. Wow, it definitely didn't change 30. So it looks like this here has changed like 3 or 4, about 3 to 4. So that change on the bottom is not a 1 change here. This is a this is like more like a 4 change. So whoa, I don't know what's going on here. I think I accidentally just exited out of my thing. Yeah, I did. Oh, dang it. All right. So go back into that. So what did we determine on this guy already? We determined that he had respiratory. We determined that he had respiratory alkalosis, or excuse me, yeah, respiratory alkalosis. And we determined now that his it was like for every 10, it was changing about 4 approximately. So we determined it was chronic. So this guy has chronic respiratory alkalosis. So now that we determined it's chronic respiratory alkalosis, the next thing we want to do here is try to see what would be the next thing we do. Sorry, I'm trying to get you to think here. So we did the pH, we did the PCO2, and now we determined that it was a chronic ratio. What do we do now? I guess we could find out the anion gap, right? Okay, so what's the anion gap equation? See if you can say what it is. What do we take first? That's right, we take the sodium. So we take 133, and we subtract it from what? That's right, chlorine. Chlorine plus what? That's right, bicarb. So what we have here is 123. So 133 minus 123 is equal to 10. So that's not much of an anion gap. So I would say this is not non-anion gap, whatever. And if there's not a big anion gap, maybe that's saying that the compensation is adequate. So yes, comp. Now, what are we going to do? We could check delta, but it seems like that's not really ever proving helpful. So let's just move on and see what the answer is here. So what is a predominant acid-base disorder? It was respiratory alkalosis. Is the degree of compensation adequate? Yeah, I think. Is there another disorder present? I don't know, not that I could see. What is differential diagnosis? Well, respiratory alkalosis. What's going on with this lady? Colon cancer. Okay. So a lady with colon cancer. That's probably going to cause some sort of maybe diarrhea or something. I don't really remember what was on my respiratory on this one here. So when a person has respiratory alkalosis, you're thinking, or alkalosis, anxiety, asthma. Okay. I think it seems like there's some other things in there too, but I can't remember what they were. Let's see what the answers are. Okay, so yeah, was right. Respiratory alkalosis. Ooh, acute. So I made a mistake there. I said it was chronic, didn't I? Yeah, I did. So let's see where I made a mistake. So you were supposed to take the change in CO2 and it was a change of, so about for every 10, the bicarb went from 24 to 22. I think in respiratory acidosis it could have been a change of one or two. Let me check real quick. Respiratory acidosis. No, huh? Oh yeah, no, this is alkalosis. Oh yeah, oops, yeah. So in alkalosis, it could be a change of 1 or 2 on this number, 1 or 2. So this top one changed 8, and the bottom one changed 3, and so that's pretty close to 8 to 4. So that's pretty close to a 2 to 1 or a 1 to 2, whatever. I guess it depends on which one I put on the top or bottom. That's pretty close to that. So you'd say that's not quite a 4 to 1 ratio. So yeah, I totally messed up there. So that's acute. Math is not my strong suit. If I can do these, you should be able to do these. And I can barely do them, so hopefully you can do them. Okay, so what's the differential diagnosis? We're going to say, so this was acute. There we go. All right, so appropriate, yes. Is another disorder present? No. Differential diagnosis, hypoxia. Oh, okay, pulmonary embolus. So what I should probably do is add that onto my list of causes of acute respiratory alkalosis. So, other causes of acute respiratory alkalosis. Oh, I just put that on my acidosis one, didn't I? Oops. Are, yeah, I did. Acute respiratory acidosis. There it is. No, this was alkalosis. What the heck's going on here? Oh, it is alkalosis. Yeah, it's like 4 o'clock in the morning right now. So, pulmonary embolus goes on my list with the other ones, as well as anxiety, pain, salicylate intoxication, and gram-negative septicemia. So I'm going to say pain, what was the other one there? They had gram-negative septicemia. Okay, good deal. All right, I'm learning here too. So next case here, we've got a 6-year-old girl, severe gastroenteritis, admitted to the hospital for fluid rehydration, and is noted to have a bicarb, high bicarb. So what's the first thing we look at here? What do you look at? That's right, look at the pH. What is it? It is alkaline, so we're going to say alkalosis. What's the next thing you look at? That's right, you look at the PCO2. What is a normal, so I'd say this is high. What is a normal PCO2? Well, 40, so that means this is high. Remember our thing? Respiratory, opposite, metabolic, equal, or same, whatever, same direction. So are these going in opposite? Nope, so it's not respiratory. Are they going the same direction? Yep, they're going the equal direction, so it must be metabolic. So we're looking at metabolic alkalosis. So what do we look at next? Do you remember? That's right. If you have metabolic alkalosis, the next thing that you're going to look at here is you're going to do a little equation thingy to find out if it is compensated or not compensated. So that's going to be the HCO3 plus 15. So what's our HCO3? It's 32. 32 plus 15. It's going to be 47. So 47. Is that equal to our PCO2? Close enough. So yes. Yes, it is compensated. Or yes, it is. Compensation is adequate. Whatever. Okay, so Now what we're going to do, and oh, by the way, that's what you do with alkalosis. The alkalosis was the HCO3 plus 15. If it had been metabolic acidosis, remember you would have done 1.5 times HCO3 plus 8. You just got to memorize it. There's no way around it. Just think alkalosis. Alk kind of sounds like elk, and so it's more simple. You just straight up add it to 15. And I'm not trying to, I don't know, whatever. Anyway, so here we go. Next thing you're going to do is you're going to check the what? That's right, you check the anion gap. So remember the anion gap equation? You take sodium, and you minus chlorine plus your bicarb. That's going to equal your anion gap. So let's do that. Sodium, 130 minus 86 plus 32. So let's add 86 plus 32. It's going to be 118. So 130 minus 118 is going to be equal to, if it was 120, we'd say it was 10, but it's minus 2 more than that, so we're going to say it's 12. And 12 is exactly a normal anion gap. So 12 is our anion gap. So this would be non-anion gap. Non-anion gap. Metabolic alkalosis. Now what do we do? Now what we're going to do is, I guess you could do the delta-delta, although I've never understood why that's useful yet, so maybe we won't do it. Okay, so non-anion gap metabolic alkalosis. So what is a predominant? Non-anion gap metabolic alkalosis. And this is kind of a silly one, so I'm going to go ahead and not a silly one. This is, well, I'm going to get to the differential diagnosis here in a second, then I'll talk about it. Never mind. So is the degree of compensation adequate? Yes, it was. Is there another disorder present? Not that I could tell. What is differential diagnosis? Now let me help you remember this silly thing. So if a person has non-anion gap metabolic alkalosis, you've got this silly picture here of this elk. And that helps you to remember that it's non-metabolic alkalosis. So metabolic kind of sounds like metal ball. So this elk has actually been shot multiple times by metal balls. So he's got metal balls all over him. Here he is. He's been shot so many times, he gets sick, and he vomits on the cushions at your house. Vomit stands for vomiting, and cushion stands for Cushing syndrome. So vomiting and Cushing's stand for metabolic or metal ball alkalosis. So there it is. That'll help you remember. That's the differential diagnosis. Why is she hypokalemic? I don't know. Vomiting? Maybe that happens in Cushing's disease. Let me think here. Cushing's disease, a person has too much aldosterone. I don't really know. I'm not sure. Maybe I don't know what the answer is, so I'm just trying to think here. In fact, this whole thing here could be not applying to this, but I just remember metabolic alkalosis and the vomiting cushion. So why is she hyponatremic? I don't know, maybe vomiting. I'm not sure what's going on here. What is she doing here? Severe gastroenteritis. Yeah, she's probably puking and stuff. I don't know. Maybe she's got two things going on. Maybe she's barfing and has diarrhea. I'm not really sure how to tell what's happening here. I think you have to use the delta-delta ratio to be able to tell if there's a secondary disorder. but I don't know. I don't remember how to work with that, so let's see what they say. So, metabolic alkalosis. Yep. Is the degree of compensation appropriate? Yep. Is there another disorder present? Nope. Okay, good. So, a patient with severe gastroenteritis has multiple reasons for metabolic alkalosis. She has been vomiting. Good job. Good deal for me. She's lost a substantial amount of hydrogen chloride. Second, the combination of vomiting, diarrhea, and decreased food intake, I don't know, puts her at contraction alkalosis, which is high levels of angiotensin II, which lead to HCO3 reabsorption in the proximal tubule, high levels of aldosterone. Okay, all right. So I guess if you have a lot of aldosterone, you're going to dump out a lot of potassium. If you dump out a lot of potassium, you're going to be hypokalemic, which is exactly what she has here. High aldosterone levels in the setting of hypovolemia can lead to potassium wasting in the late distal tubule. In addition, potassium can cross some cell membranes in exchange for hydrogen to help blunt the acid-base disturbance in the blood. Why is she hyponatremic? She is likely suffering from hypovolemic hyponatremia, most often caused when too much GI fluid loss is replaced with free water. Okay, so 75-year-old man with morbid obesity is sent to the emergency room by his skilled nursing facility. However, after he developed a fever of 103, so I'm already thinking septicemia. I haven't even looked at the numbers yet, but it seems like there was this thing that we memorized that was metabolic. Let's try to remember here. If you want to aggravate your MAW. Remember earlier was you want to nag your MAW. This is if you want to aggravate your MAW, which is anion gap metabolic acidosis. If you want to aggravate your MAW, you want to go play in your mud piles to get all dirty, because that would really aggravate her. Mud piles. I don't even remember all these things. That's like methanol. This is like ethanol. That might be like septicemia or something. That's like, no, this is lactate. Lactate, I guess, builds up when you have a septic infection. I don't even remember these other ones, but I know where I can find out. My little cheat sheet here. Here it is. Methanol, uremia, diabetic ketoacidosis, peraldehyde, iron, lactic acidosis from septicemia, ethylene glycol, and salicylates. So I'm already guessing this guy's got septicemia because I looked at him and I saw he had a fever. Now, I haven't even looked at any other numbers, and I would already say he probably, just because he's septic, I could say that he probably has anion gap metabolic acidosis. Let's test my hypothesis to see what's going on here. So, pH, remember, that's the first thing you look at. Is that high or low? That is low, which means he's got acidosis. So far, that matches up pretty good with my metabolic theory. Now let's look at his CO2. His CO2 is, so this was low. CO2 is above 40, right? So that's high. So those are in opposite directions. So if these are in opposite directions, then he's got metabolic. Nope. I mean, if they're in opposite directions, respiratory opposite, metabolic same. So if they're in opposite directions, then that means that he has something respiratory. Respiratory opposite, metabolic equal. So his primary thing is respiratory. So that does not match up with my guess here, which is fine. I was just throwing that out there. So respiratory acidosis. So he may have a secondary one. We'll find out here. So he's got respiratory acidosis. This is primary disorder. Is it acute or is it chronic? Well, if we do respiratory acidosis, then the thing that we're going to do to find that out is we're going to say, okay, it would be 1 for acute and 4 for chronic. So CO2 has changed 10, and the above normal, so it's gone up 10, and his HCO3 has changed. Wow, normal is 24. So yeah, that for you'd think that would have gone up. So I would say we probably have two disorders going on here. So that's all kinds of messed up. So probably acute, although I don't know. Because that's gone down. So definitely messed up. Okay, so that means this guy's probably got two things going on here. Which maybe one of them is going to be the anion gap metabolic acidosis. So let's see if he has an anion gap. So remember how to do that? That's right. We take 138, which is the sodium. We subtract chlorine from it, which is 99. And the bicarb with that as well. So 99 plus 15 is going to be 104. So basically 103 minus 1, or 138 minus 104, which is going to give us 34. So 34, or 114, 24. Sorry. Okay, so 24, normal is 12, so that's like double 12. So this person does have an anion gap. So if they have an anion gap, gotta see if there's a secondary disorder going on here, and I think that's where the delta comes in. Although I don't even know how to use that yet, so we'll see what happens here. So for the delta, they say to take your well, actually, if you have an elevated anion gap, you just know right away that they have. You can just basically say, I think it was if it was greater than 30 or less than 24. I can't remember, but anyway, if it's elevated, then you pretty much can just say straight up that they have anion gap metabolic acidosis. So that does agree. So they have anion gap metabolic acidosis, and that's their number 2. So this is their primary, this is their secondary. And I guess you could do a delta ratio here, but I'm not sure what that's going to tell us. So let's do it and find out. So what you do for this one is you take the measured anion gap, which is 24, and you subtract it from the normal anion gap, which is 12. Then you take the normal HCO3, which normally HCO3 should be 24. Subtract from what we actually have for an HCO3, which is 13. So that ends up being 12, minus 12. So that equals to 12 over 11. I don't know what that means, but there it is. There's our delta. So anyway, yeah, so I'd say this guy's got secondary anion gap metabolic acidosis, primary respiratory acidosis. Let's see what they say here. So predominant respiratory acidosis. Degree of compensation adequate. Oh, I didn't even do that. Compensation adequate. No, I don't think it is, because he had a huge anion gap, remember? Is there another disorder present? Yes. It was anion gap metabolic acidosis. What is the differential diagnosis? Wow. Okay, well, I definitely had the septic thing going on there. So I think he's got some sort of septic thing. Plus, his blood pressure is super low. So I don't know what else he could have, but he has at least that one. Let's see what it says here. So, respiratory acidosis. Okay. So they say probably chronic. And let's see if that matches up. I was thinking, I don't know, maybe acute, but let's actually do it now. So that was a change of 10. And I guess this next one, HCO3. So 24 is normal. So for every one change, there should be a change of 4. And this is down like a ton. It's down 11. So that's more like a chronic. Anyway, hopefully you're kind of getting the hang of what's happening here. And there's some more here, but I think we've got the general idea of what's going on. So I may finish up here in a second. But so is it appropriate? No. That's what I said. Is there another disorder present? Yes. That was what I was saying. And get metabolic acidosis. Differential diagnosis. Respiratory acidosis may be due to some chronic undiagnosed problem and not due to the chronic undiagnosed. Yeah, okay, whatever. Yeah, so COPD, maybe he's got COPD or obesity, hyperventilation syndrome. So respiratory acidosis, COPD should be on my differential here. Let's see if I have that. Respiratory acidosis, COPD and high bicarb. Yeah, there it is. And I think that's about done.